turn off my camera, so we will have more bandwidth. Okay. Michael, could you just confirm that you are seeing my desktop?
Yes.
Okay, nice. So we are ready to start. So welcome everybody. Thank you for joining this evening. I'm talking about business analysis with Transact SQL. I'm Dan Sarka. I'm quite a long time in this community, got 35 years of experience, and I authored, co-authored 18 books so far, more than 20 courses, etc. So what I will talk about is quite advanced Transact SQL. So I do expect that you are already familiar with Transact SQL language with, of course, basic select statement, but also a little bit more advanced, like I guess you all already know, window functions. And I will talk about quite tough problems, and we'll show you that even for advanced analysis that could be already treated as data science, you don't really always need R, Python, or some other tool. Many things can be done, of course, if you know how to do it, also in Transact SQL. So I will explain what is relational division. The problems will go from quite simple to more and more complex. And then I will talk about ABC analysis, survival analysis, market basket analysis. Then I will introduce lookalike model and finish with Bayesian inference models. So let me immediately start with relational division. We will have a lot of code. It will be quite intensive and long session, so I will start immediately with relational division. First, a little bit of formal definition. This relational division is one of the basic operators that was already defined by Mr. Cod when he established the relational model. However, it is not really frequently used and definitely not well understood, and I will show when it can be useful in terms of business analysis. So formal definition: a divisor relation partitions a dividend relation to produce a quotient relation. Dividend and divisor are in many-to-many relationships. So the quotient is made up of those values of an attribute from the dividend relation for which the second column of the intermediate relation, the one that is the resolution of M-to-M relationship, contains all of the values from the divisor relation. Wow, this sounds very, very complex, but it's not that complex. So we have dividend is the relation ABC on the right side of the slide. Divisor is XZ, and they are in many-to-many relationships. So we have intermediate relation that represents this relationship, and you can see that the value A from the dividend is connected to all values from the divisor, X and Z. So value A is connected to X and connected to Z. I'm not interested in A and Y. And value B is not connected to Z, and value C is not connected to any of the elements from the divisor. So the quotient is value A, or a set that consists of a single row, which is value A. How does it help us? Well, for example, we can search for customers that purchase every single distinct product. I would just like to give a small warning here. This is many times misunderstood. If the divisor relation would be empty, in my case XZ, if it would be empty, then the result would be ABC, the complete dividend relation. This is mathematically correct. However, it makes no sense in real life. Let me give you an example. Let's say that we have a bar where we have maybe 10 guests, and there are some waiters. Now we are searching for guests. Okay, please turn off the microphone, everybody except me. So we are in bar and we have guests and waiters, and we are searching for those guests that have been served by every single waiter. Now, what happens if there is no waiter? The result is all guests, which means logically you cannot find a guest. You cannot find a guest for which you could find a waiter that didn't serve this guest. Of course, because we don't have any waiters, this is kind of empty condition through an empty relationship. But in real life, of course, you are not satisfied. Theoretically, every single guest was served by all waiters. However, nobody has beer to drink. So I usually say additional condition, the divisor relation must not be empty. Then you get meaningful results. Okay, let me start immediately with demos. So I will go to Adventure Works DW 2017 database. First, I will check all of the sales I got, fast internet sales, fast reseller sales. And this is something I will prepare a little for later for survival analysis. And let me analyze this data over years. And I see that I have years 2011, 12, and 13 pretty full, while I have 2010 only December and 2014 only February. So I will just create two views where I will just select the rows where year order date is between 2011 and 2013. So I'm excluding these 2 years, which are kind of exceptional. And now I have a little bit less rows, but or at least the data is more or less consistent. So I have now through views rows for 3 years only. Now relational division. In this case, I am searching for all customers and number of distinct product categories they purchase. I'm joining fact internet sales to dim product and through product subcategory to dim product category, and I'm excluding components. Components are not selling; they are just components for the retail products. So let me check customers and the number of distinct product categories. This is just the first name of one of the categories. So customer 11,000 has purchased products from all 3 categories, while at the end, some customers, like customer 29,481, purchased only something from category bike. So let me select those customers that purchased products from all categories. So I am just calculating count distinct English product category name and want to have the same number as I have distinct product categories in the dim product category lookup table without components which are not selling. And these are my customers that purchase products from all categories. So I could say these are my best 2,000 customers in a way. So of course, this was pretty basic, not a big deal, but still might be interesting. So let's go to the next problem, ABC analysis. Again, let me start with a formal definition. This is a categorization method in which an entity set of an interest, like customers' products, is simply divided into 3 categories in descending values. So A is the best category from business perspective, B is the middle, and C is has the lowest value. And typically, A items, 20% of A items contribute up to 80% of the profit. This is kind of well-known rule. So this Pareto principle, 80-20, is just a specific example of ABC analysis, where you simply group B and C items into a single group rest, right? Those 80% that contributes 20%. Okay, so let's do this with some querying. So I'm searching first customers by number of order lines. So not by profit, but maybe simply by number of products they order. So I am calculating absolute frequency and also relative absolute percentage. So this is absolute frequency, how many order lines I have per customer, and what is the percentage of total order lines. And now I will use this intermediate result to calculate also the running totals. So sum of absolute frequency of orders by absolute frequency descending, and also I will calculate running total for percentage and order by this absolute frequency descending. So my customer 11,300 has 67 order line items, which is 0.1%. And then the next customer, the second best, has 65 order lines, and altogether this is already more than 0.2%. So now I would need to make a split somewhere at 20% of the customers, and then see if they contribute cumulatively percentage is 80%. However, turns out that order lines are not the best thing to analyze. Of course, we want to analyze sales amount or profit. So let's go to and analyze product models. So I will rank product models by sales amount. So first I'm unioning my views for internet and reseller sales, and then I am calculating sum of sales per model name, and then calculating rank over these products, and running total and running percentage. And let's see what I get. So now you can already see interesting score. First couple of models actually contribute a lot. So you see in sales total, running percentage is above 80 already with the 11th product. So first 11 products out of 107 already contribute more than 80% to the total sales. So this would be my A group, which is even less than 20%. Okay, ABC analysis is still simple. So let's add time to our analysis. So I'm talking about survival analysis. Survival analysis is about estimating the lifespan of a particular population. Or you can look to it from the other perspective, also time to event analysis. So estimate the time for an individual or a group to start or to experience an event. So let me make a concrete example. Lifespan, let's say that you have subscribers to some of your services. So lifespan is estimating how many years, months, days your average customer will be with you. Or time to event, how many days will customer be with you before customer will leave you. Also, this is very well-known measure for machines. Mean time between failure also is very, very similar analysis. Now, if you don't have subscriptions, name subscriptions, then you have a little bit more problems because the subject can enter and exit at any time in the study. And the problem is, how do you define that the customer has exited? So this must be somehow an arbitrary decision. Now imagine that you have a customer that made 3 purchases in 3 months, and now this customer didn't make any purchase for a year. It is your decision whether you say that this is already customer that abandoned you, left you, or is this customer still active? So you must actually check many different possibilities, many different time points and lifespans before you find the best option, the option that is the most realistic for you. However, sometimes you might also have control about this exit events at least, because, for example, if customer didn't pay you the last invoice, maybe the customer has exited because you threw the customer out of the system. You simply banned sales to this customer. You might have even a variable that indicates this event. Was this churn voluntarily made or involuntarily? Voluntarily means did the customer make it or did you make it? So survival function defines the probability that the event of interest has not occurred at time t. So churn has not occurred. And the probability of survival after time t is the thing that we are measuring. So, well, for example, we want to know what is the percentage of customers that stay with us for more than 2 years, for example. The hazard function is the probability that the case will experience an event of interest within a small time interval, maybe within a day. So this means that you are searching which time intervals are the most hazardous. These are intervals when most of customers leave you. Depends on the different types of businesses. You might notice very, very important time intervals when customers decide to leave you. So if you have like monthly paid subscriptions, then of course, if you do this on day level, the first day of the next month or the last day of the current month is the critical time point. But even in retail sales, you might have some better days, worse days, some days where more customers tend to leave you. So you should be especially careful with those days. And of course, don't forget, I'm telling you an anecdote that really happened to me. So there was a restaurant chain and they did a hazard analysis and they realized that the very critical day is Tuesday. And of course, they forgot that on Tuesday, all of the restaurants from the chain were closed. So yes, that was normal that the customers didn't come on Tuesdays, right? So let me do this analysis on my data. And as I said, this is kind of arbitrary decision. So I have 3 years, 2011, 12, 13. So let's find customers that were active in 2011 or 12, but they were not active in the last year of my data. So I'm searching all customers for which there is something. They have some orders, but the max order date is more than 1 year away of the last date that I have in my database. And you see, the first customer I have, Sydney Rogers, that made a single purchase on, or maybe more purchases, but this is the only date when this customer made purchases on 2nd of January 2011. And there is already 730 days difference from the last purchase till the beginning of year 2013, which I decided to make my cutoff point. Now, as I said, cutoff date is arbitrarily selected. And for example, I decided not to use 1st of January, but 1st of March 2013. Maybe I have something important happening. Maybe my fiscal year starts on 1st of March. So I'm not really interested in New Year or calendar date, but this day. And let's find all customers that stopped purchasing after this date. I have 414 customers that purchased something, but not after 1st of March 2013, and this is the last date when they purchased something. And tenure days means how long were they active? How long were they active before 1st of March 2013? Now I will create a table for this, and I will call those who left me after 1st of March. Those are those that succumbed to risk. And I will arbitrarily add the reason. I will say that 2/3 of them left voluntarily and 1/3 involuntarily. Imagine that this is some real data. And so I will add also stop reason. These are my 414 customers that left me. And now I will also insert active customers. So active customers are those that have some purchase after 28th of March 2013. And they have no purchase before that. And they have purchases before that. I'm not interested in completely new customers here, customers that never purchased before 1st of March 2013. So I have more than 6,000 customers that have been customers before the cutoff date and are still active. And let me add the primary key to this table and check the data. So these are my customers. Those who have stop date are succumbed to risk, so they left me, and voluntarily means customer decided to leave me, and this I means that I decided that I will not sell to this customer anymore. These are minimal start date, maximal start date, and minimal stop date and maximal stop date. So some person even left me on 28th of February 2013, one day before cutoff date. Now let's calculate hazard probability up to 365 days. So I am summing all cases where tenure days is lower than 365, and for those I'm adding 1 as 0, and I'm also calculating the average. So average of for each one that is active, I'm adding 100%, otherwise 0%. So this is hazard probability up to 365 days. I have this is tenure cutoff, the population, all of active and those that succumb to risk. 183 are those for 1 year, and this is 2.67%. So this is one analysis. I can expect that after a year, less than 3% of customers will become inactive. Now, the opposite, I will analyze survival, customers that survived at least 365 days. So I'm again checking those that are active for less than 365 days, more than 365 days, and then those that succumb to risk and those that are still active. And again, also average based on some cutoff date. Right. So I have 232 that succumbed after 1 year and survived at least 1 year is more than 91%. More than 91% that stop, that start purchasing, survive over 1 year. Now it's interesting to find hazards for every single tenure length in days. So how many customers left me directly after 1 day? So I have one customer. There are 41 customers that made purchases in 2 consecutive days, and one of those left me. Now let's see if some days are more critical. With this one, So after 15 days, like 2 weeks, I have 3 customers that abandoned me. Now I can calculate this day by day, order by day, and calculate also cumulative values, and find the most critical time point. So this is cumulative, so tenure up to 3 days, already 3 customers left me, which is 0.04%. And I still keep 99.956% customers after 3 days. And I can try to find those dates that are especially critical when there is big race of customers that left me. So this is survival analysis. And then you can do additional analysis of those that succumb to risk. This is then up to you. This is nothing special. So for example, I have stop reason, and I can analyze this over stop reason. So how many orders I have for involuntarily stop, what was total profit, and I see that percentage is higher for those that voluntarily left me. Okay, I will not say that this is because those that involuntarily left me didn't pay. It's a complete coincidence, because remember, I didn't really care about this data. I just created an artificial variable. But I can analyze what is this amount of customers based on many different input variables. For example, number of cars owned, region, and I can try to find which is the most important region. So for example, customers with 4 cars from North America give me quite high profit. Also customers with 3 cars from Europe, even higher profit. So these are the customers that left me, and these are the groups that hurt me the most. Or I can also check this by region and number of cars owned pivoted. Then it's even easier to see some things. For example, it's interesting, this sale, nobody from Europe with 4 cars left me. So this seems like extremely faithful group. And now you can play more with this survival and hazard function. But I will switch to a little bit more complex problem, classical market basket analysis or association rules algorithm. Which things are solved together? So first we have to make again some definitions, how we will measure the strength of this rule. So let's say an item set is a combination of items in a single transaction. For example, 9 items in a single order. So first we scan through the data set and try to find item sets that tend to appear together in many transactions. And we simply calculate or count how many times this item set appears and compare this to the total number of rows. And we call this support. So support for item set in cola and frozen pizza in these 5 transactions is 0.4. We have 2 transactions with this combination out of 5. So the higher the support, the stronger the rule, right? This sounds quite logical and quite simple. However, is there an order in this rule? Is it really the same if you have first frozen pizza and then cola, or is it order important? Take a look at the combination in transaction 2, milk and potato chips. This combination appears in 1 transaction out of 5, so support is 0.2. However, milk appears in 3 transactions, 1, 2, and 4, while potato chips appears only in transaction 2. So we can say that whenever there is potato chips in basket, there is also milk in basket. But the opposite is not true. Whenever milk is in basket, it's not true that there is also potato chips in the basket. So the point is that we should calculate confidence of the association rule. So this is support for the combination divided by the support for the condition. So support for the combination milk and potato chips is 0.2, and support for milk is 0.6, and support for potato chips is 0.2. And this gives us a confidence of 0.33 for the rule. If customers purchase milk, they will purchase potato chips, and confidence of 100% or 1 for the rule. If customers purchase potato chips, then they will purchase milk. Actually, this second rule is much more significant and much more important. We can maybe even define order of items. This really depends on the type of business. So if you have, for example, internet sales, then you have orders of line items in the basket, because you can follow how a customer edits items to the basket. If you are a retail store, then of course at the cashier, the order is completely messed up, so you cannot rely upon order. And then you might even define sequential association rules. Maybe you can even find your own ordering variable. Maybe you can define it through some date and time column, or simple sequential number. But you must be sure that this is really the order of items in the basket. Otherwise, items, how they were added to the basket, not how they were counted at the cashier. So if you are not sure, then you shouldn't do order association rules. Now, you can imagine that all algorithms that I'm representing, I try to solve them without any loops. Of course, if I would need loops, then it wouldn't make sense to use Transact SQL. Turns out that I don't need any while loop or any cursor. However, what I will use here will be apply operator, which is kind of Transact SQL loop. Let me show you this. So first, I have two tables. I have two views in this database, and I will just materialize them because I want to have as good performance as possible, and I will show you the content of these tables that I just created. So I have orders, where I have basic things about orders. So this is order number, customer, and some additional data from the customer dimension. So I will have possibility to do some more advanced analysis. And these are just line items. So I have order and I have line number, and these are internet sales only, so line number makes sense. I am not using reseller sales, and this is the model. So here I have these combinations, Sport 100 with Cycling Cup, Sport 100 with Road 350W, and Cycling Cup with Road 350W. Now I can start calculating frequencies of item sets with a single model. So this is simply count of rows or line items for a model. So Sport 100 is the most popular product, and then it's water bottle. Now I can start doing this from negative perspective. So for example, I'm interested which models are not associated with anything else. Models that are purchased only once in a single order. So I will just count from order line numbers, distinct order number, and it must be equal to count of all distinct order numbers must be equal to 1, and count of distinct models must be equal to 1. So these are models that are not associating well with other models. However, this doesn't mean that this is the absolute truth. Water bottle was, on the other hand, extremely popular product. So apparently, it is because it is so popular, it also appears many times alone in a single order. Probably some customer just forgot water bottle at home and stopped by and never returned to our store again. Of course, we can try to find out how this works over region, since we have this data, and see in which regions I have customers that come to me only once for which product. So especially in North America, people just come and pass by and take water bottle. Okay. I can also do this pivoting by income group. This is just another way how to analyze the same data, and maybe I see some again some interesting patterns or interesting groups. But let me go now to the positive approach and find those products or models that tend to appear together. So first, I will check frequencies of item sets with two models. First, I can start by using joins. So I'm joining line items to themselves based on order number from the left equals order number from the right, and the model from the left is greater than the model from the right, could be also lower. I'm not interested in order yet. So water bottle, mountain bottle stage, it has really high support. So we have nearly 1,000 line items with this combination, and you see water bottle does also well with rose bottle cage. So it's really true what I mentioned earlier. Water bottle is not so negative product. It's just so popular that appears many times also completely alone. Now I will do the same thing. Just this time I will do cross apply. So I will have line items and then I will cross apply to tabular expression. So I simply express join with a tabular expression. So this is actually completely the same, logically completely the same query. Also, performance is the same. SQL Server, I will not even show the execution plan, just take my word for it. SQL Server will make completely the same execution plan. However, I prefer apply because then it's very easy to add a third model. So I'm searching now. So now I store this in a common table expression, item sets with two models, and then with another cross apply, I'm adding the third model, right? So now I can find item sets of three models, which are the most popular. This is much easier to write than with join. And I see that mountain bottle cage, mountain 200, and water bottle is the most popular triple, right? Nice. Let's now actually express the rule. So now my condition for apply or for join is not just model from the left greater or lower, but just different. So I want to find both rules, like milk, potato chips, milk. Of course, the support will be the same, but I will also create a rule as a string. So let me show you this query, and I have the rule. If customer purchase water bottle, then customer purchase mountain bottle cage. These are the two models involved in this rule, and support is 993. And you see the same support is for the second rule, which is just turn around, mountain bottle cage, then water bottle. Now, why I need both of those rules? Because I want also to calculate the confidence. So I want to add the confidence. First, I find all pairs, then I find all rules, and then I count distinct models. So this is count of models, right? Count on how many orders this model appears. And now I can calculate confidence for both rules, and I can order by support descending, and then for the same support by confidence descending. And now I will find some interesting rules. And I see that mountain bottle cage water bottle rule has the same support as the opposite, right? However, confidence is 83%, while the opposite rule, water bottle, then mountain bottle cage, confidence is only 40%. So mountain bottle cage explains water bottle much better, and probably this is the product you want to force because you expect to sell more. People will not forget the water bottle when you have mountain bottle page, while the opposite can happen easily. This is already quite interesting. But since I have also the sequential number, line items are sequential, then I can just add additional condition that line number from the left, when I am applying this tabular expression on the right side, must be lower than line number of the right side. So I will check only those pairs which appear always in the same sequence, and then express all of these rules. Now for each pair, I will have a single rule, and the maximal support is lower because, of course, I skipped those where the rule was turned around. So this is the rule with order. The most important rule for this order, the most important rule with order is mountain tire tube and then sport 100. Or probably this one might be even more important, mountain bottle page, then water bottle. Support is just slightly lower, but much higher confidence for this order. In this case, we also get the order. Now it looks very nice, logical, and maybe you are already happy how you will implement this in production. Of course, turns out that association rules are not so useful as everybody thinks, because remember this first rule, most important rule, mountain bottle cage, water bottle. Yes, what else would you expect? I mean, if you have a bottle cage, you probably won't buy a car, but you will buy a bottle that will fit into this cage. And this is the problem with association rules. When you see the result, let me go back here and check the result again. When you see the result, if you are not familiar with first 10 most important rules, if you're not familiar with them, forget about the result. Something is wrong. Either something is wrong with analysis, or something is wrong with you, that you don't have the clue what you are selling. So you should have the feeling. And the issue is, where can you find then those interesting rules? You have to go a little bit down. Many times people say just skip first 10 or 20%. Again, doing some kind of manual ABC analysis, just throwing first 20% away, because they should be the rules that you are already familiar with. And the problem here is, the big problem is that in a retail store that has hundreds of thousands of products, you get billions of association rules, and this is simply impossible to make a good overview. Fortunately, most of the time you use these rules just in application for recommendation system. But if you want to learn something new, it's kind of hard to find these golden nuggets in this big sandbox. All right. Now let's continue. We have two more algorithms, pretty intensive. So first, I will come to lookalike model to idea for this model through two other algorithms. So I will create kind of lazy decision trees. So actual decision trees are using recursive partitioning to build the tree. So they split data into partitions, and then they continue splitting in such a way that you get more and more clear distribution of the target variable. And then the problem is how to measure the purity, and another problem is where to stop. Decision trees usually can easily overfit and give you results that are too good to be true. Let me show you this graphically. So I have some customers that are satisfied, some customers that are not satisfied. Initial split was done over age, and then I can do another split over education, and I get purer and purer classes. And then maybe I can cut off useless branches. And then I have a new model. And then I search through this tree to see in which class this model belongs, to which class this new case belongs. And then I simply read the distribution of target variable in this class. So for example, if I have a new customer that is older than 35 years and has education level greater than 2, then I have 87% probability that this customer will like my product, whatever it is. So this is very, very short introduction to decision tree. And let me also do a very brief introduction to k-nearest neighbors, KNN algorithm. This is completely lazy learning. There is no training at all. So simply you take a new case and then you select k cases that are the closest to this case based on input features or input variables. And this usually works on geometric distance, so you must have numerical data with z-score normalization. You must have data on the same scale. Graphically, this is new case. So for example, you are searching for the 3 closest cases or 8 closest cases, and then you calculate the average of the target variable. What is lookalike modeling? This is kind of combination of decision trees and KNN. So we can use it for discrete variables as well. And instead of doing all of this development of decision trees model with hundreds or thousands of iterations, we calculate distribution of target variable in classes just for the lowest leaf level of the tree. So we just calculate those and do this in a single pass. So it's not so lazy. It's not so lazy training as KNN, which doesn't do any training at all, but you do all training by a simple single pass through data with a single grouping. And then you just use the KNN logic. However, instead of going to the source data, you go to the aggregated data and try to find to which group the case belongs. Some results might be worse. For example, here in the slide, if you look at this intermediate level on the left side, we have quite pure class. 73% of customers like the product, 27 didn't. But then if I go down to the right with education 2 or less, the distribution is 33-67, actually less pure. Decision trees wouldn't use this class, would go also and assign a case from this class, maybe a branch higher, stop developing a branch higher. So you get a little bit less accurate results than with actual decision trees. However, you do train the model with a single pass through data. And let me show you how this goes. So I will create a single numerical index from string and ordinal variables and from nominal variables and discretized continuous variables. So I will have numerical values for every single input variable. So for example, I will have education and will create numerics out of it. Also for commute distance, occupation, region, and then I will use entire function for continuous variables to get also numerics. I can also make whatever different groupings. So for example, I will just have children and I will say 0 if the value is null, and I will just group cars 3 and more to a single group. So this is part of data preparation, and this can be done in different ways, and you should actually try in different ways and measure the results, measure the accuracy. So these are my input variables. Now I want to store these things somewhere, right? And I will, from these input numbers, I will just create strings, concatenate them, and call this grouping factor. So this is grouping factor common table expression. I will calculate grouping factor. And then I will simply group by grouping factor. Let me show you this logic. So I have all of these input variables, right? And for every single input variable, I calculate those that are interesting. I calculate numbers, and then I concatenate these numbers to a single grouping factor, simply adding them. And let's group by this grouping factor and order by count. And here are my groups. I made grouping factor out of 4 variables, and this is count. Anything which has less than 10 cases is basically useless. Some groups are simply useless. However, most of the groups are pretty useful. Most of the groups have enough cases. So if I have too many input variables, then this count would be too low in many of the groups. So the model wouldn't be really useful. Now, let me create the training table. So I will split data in training and test set. I will use test set to calculate the accuracy of my model. And I'm adding the grouping factor, so 30% to test set, using crypt-gen random cryptographic function. By the way, this gives you much better randomness than UID. Don't use UID for this task. Crypt-gen random gives you really random things. And I will select the rest of 70% of rows to training set. And I will index my training set, so my queries will be faster. And now I can just search for lookalike cases from test set into training set and calculate the prediction for the target variable. Calculate the probability, right? And if probability is greater than 0.5, I will say this is potential buyer, otherwise not a buyer. And let's see the results. So you see there was practically no training, and I got the results. So this is buyer and this is predicted. And you see some are correct and some are incorrect. 0, 0 is correct, 0, 1 is incorrect. And what is the accuracy? Let's calculate the accuracy. So I will just compare the actual and predict it. And here I have, these are true negatives, these are true positives, these are false positives, and these are false negatives. So let me calculate these numbers. So I have true negatives, and I have true positives, divided by the total number of cases. And I get my accuracy, in this case, 63%. This doesn't look very impressive. However, let me tell you that initially I have approximately 50-50 buyers on buyers. So if I use this lookalike model to select potential buyers, I'm actually getting quite reasonable lift. Many more buyers. If I just focus on those true positives, I will target many more buyers than using random selection. Also, the data is actually even too much randomly distributed. I tested even the best, I tested also random forests and other things in R on this data set, and I could never get more than 70% accuracy. Now think of it, without any iteration, with lazy training, with lazy and everything, and just in Transact SQL, I get something that is completely comparable to R or Python, not much worse. And I can do the same thing with a different approach. So again, I have a predictive target variable, and I want to use Bayesian inference or naive Bayes model. However, I want to create this in Transact SQL. Now, the approach here is just the opposite to lookalike model. In lookalike model, we searched for the group and then checked the average of bike buyer, the probability for bike buyer. So we calculated the probabilities of target variable in groups of input variables. With Bayesian inference, you do something the opposite. You calculate probabilities of input variables in classes of target variables. How does it help? Let me quickly explain this on an example. Imagine that you are buying a second-hand car, and from experience or from magazine, you realize that 30% of second-hand cars are faulty. Now you have a friend that is a better mechanic than you, and you manage to get this friend to take a quick drive with you, and then this friend declares whether the car is good and faulty. Of course, even this friend is not 100% accurate. Out of 90%, out of 30% of faulty cars, 90% of them identifies correctly as faulty, but 10% incorrectly as good. For good cars, the friend is probably not too optimistic. 20% of times, the friend will declare a good car incorrectly as a faulty one. Altogether, friend will judge 41% of cars as faulty and 59% as good. Now, how can you use this? Well, you see, out of this 59% judges as good, 56 were really good. We can just then normalize these things. We can just normalize to 100. And if I normalize to 100%, I see that out of 59% cars declared as good, 95% were actually good. Now, this is the result. When I do the reverse tree after the classification, the posterior probabilities are much more accurate than the prior probabilities. Or, to go back to the example, initially I had 70% of chances to buy a good car. After my friend declared it as a good, my chances have risen to 95%. This was just a single input variable. What if I have more than one input variable? Then I have a problem. Then I have, for example, this problem color, class, and weight, and I'm searching whether there is a connection between missing values. So if color is missing, 80% of weight values are missing as well. If class is missing, 50% of weight values are missing. So joint probability is 0.48. And probability or likelihood, this is not probability, we have to standardize it, normalize it between 0 and 1 to get probability, so this is likelihood. Likelihood for color missing for weight not missing and class missing for weight not missing is 0.08. So apparently if color and class are missing, then weight is probably missing as well. Now we have to convert likelihoods to probabilities by normalizing their sum to 1. And I see that the probability that weight is missing if color and class are missing is 85–86%, and the other is 14%. And then, of course, it gets more complex if you have 3 or 4 or more variables. So let me go to my example. I already have training and tested, so I have also, one row too many or couple of rows skipped. Let's execute the whole query. So I have my training, my test set, and I have some input variables. I will use these input variables for Bayesian inference. So calculated a single input feature distribution. Target variable is bike buyer. So for bike buyer equals 1, right? So I'm calculating this distribution. And for bike buyer equal 1, I have 46% of people from North America, nearly 24 from Pacific, and nearly 30 from Europe. This is just for a region where bike buyer equals 1. And of course, then I have to do the full calculation to do also this for region, number of cars owned, commute distance. This will be input variables I will use. And then I have to repeat the same thing for bike buyer 0. Grouping sets becomes very handy here. So these are distributions of input variables in classes of target variable. So commute distance, and then number of cars owned for bike buyer equals 0, and then region for bike buyer equals 0, and then commute distance for bike buyer 1, and so on. So this will be my training data. Now I will create a model by actually calculating this. I will select into these groupings for bike buyer equals 1 and for bike buyer equals 0. And this is actually my model. This is now my naive-based model. Now, how do I calculate the posterior probabilities? Here is an example. So I have rows for region Pacific, number of cars equals 1, and or commute distance 2 to 5 miles. And these are the probabilities for bike buyer 0 and bike buyer 1. Now, how do you calculate? Remember, this was formula from the slide. Now, let me calculate this just for number of cars 1 and the region Pacific. I will not even use commute distance. So I have first number, and let me copy it twice, and this is second number. And I need these two numbers. I'm following the formula only for two input variables. So this is then probability for state 0. And then I could calculate also probability for state 1. So if number of cars equal 1 and region equals Pacific, probability for state 0 is 0.33. Now, let me go back to the previous query and let me check again what I did. What I did is, you see, I multiplied for one value with another. I'll multiply across rows. I multiply this value with this value. So this is kind of aggregation, but I don't have aggregate product function. What I need is aggregate product function, and then it would be easy to calculate this probability. Unfortunately, there is no aggregate product function in Transact SQL. However, I can use a little bit of mathematics, and remember that if you sum logarithms of values, then you are actually, this is the same thing as logarithm of multiplications of the values. Simple mathematics with warning, logarithm is defined on positive numbers only, but here we have probabilities between 0 and 1. We have positive numbers. 0 could be the only problematic one. If I would have somewhere probability 0, I would have to take into account also this case. Now, let me show you how I can do now predictions from a model. So I will calculate negative, positive percentage. I'm searching for the model where backfire is 0 and the region is specific or number of cars equal 1 or commute distance 0 to 5 miles, and then calculate the negative probability or negative percentage, and the same thing for positive percentage. And I can calculate all of these things together with a little bit help of mathematics. So I have 72% probability for what was should have column names. Positive percentage, negative percentage. Okay, so first is positive and then negative. So in this case, I have nearly 73% of probability that this person will be a bug buyer. Now I can do this in a query, right? I can do this in a query instead of variables, but still this is a query for a single person. So this is true percentage or probability for value 1. Now, if I use the parameterized query, I can create the function. I can create the function that will be used for prediction. And what can I use then is, again, apply operator. So I can apply this function on every single row from the test set and get the predictions. And these are predictions from the naive Bayes model, the actual value, the predicted value. Again, you see that some values are correct, some values are wrong. So let me calculate the accuracy again. And again, I have true negatives, true positives. Let's do the calculation. And see how does it compare to lookalike model. Check the accuracy. And accuracy is 60%, still not bad, slightly worse than lookalike model. However, still quite good for a very, very simple and transact SQL. I mean, not so simple for transact SQL analysis. And this is more or less this what I wanted to present. I think it was quite intensive, but the point is that you can, of course, do a lot with transact SQL. Transact SQL is not obsolete. You don't need R, Python, or Azure machine learning for the simplest things. And definitely transact SQL and SQL Server will be magnitudes faster. I mean, with R and Python, you typically work on samples, while here you can analyze with these queries also huge amounts of data. So it is definitely quite useful. And it's just not so, let's say now, it's very fashionable to talk about machine learning. And if you say transact SQL, people think that you live somehow in the past. However, these things are doable also with transact SQL. The point is that I didn't want to go to any loops, but still I managed to get quite advanced analysis. So let's see just, I think we have some time if there are any questions. Before that, okay, we'll see if this will work. If this will be live event at this moment, we still hope that it will be live. SQL Saturday, Slovenia in 2020, in Ljubljana, December 12th. And one more thing, we calculated the accuracy. I want to finish also with a joke. I think the majority here will understand. The majority is from Balkans. So when you get low accuracy, you simply pronounce it accuracy. And now I'm ready for questions.